Hi there. I will show you today how to use Excel in order to do the ANOVA statistical procedure. The ANOVA is a procedure in statistics that compares more than two means. As you recall, the t-test was the procedure that compared only two means of the independent variable, while the ANOVA now gets over this shortcoming of t-test and compares more than two means at the same time. Here in Excel, I have this data set. I have 2012 SUVs with 4, 6, and 8 cylinders, and we have a sample of 7 cars for each engine size right here on this table. So for 4-cylinder, the cars are right over here on this column. For 6 cylinders right here in green, and for 8 cylinders is right here in the light blue. Now, what do we want to do here? The first thing is the set of hypotheses. Do we want to test something? Yes, we do. So the null hypothesis is that the means of fuel economy of SUVs for all 3 engine sizes are equal, meaning that the mean miles per gallon for 4-cylinder is going to be equal to the mean for 6 cylinders and equal to the mean of the engine size 8-cylinder. So in other words, there is no significant difference in the miles per gallon that each of these 3 engine sizes will produce in terms of the fuel economy. Now the alternative hypothesis is the opposite to the null, where in the case of ANOVA we would state that at least 2 means are significantly different, or at least 2 means are not equal. So the mean of 4-cylinder would be different from the mean of 8 cylinders, or the mean of 6 cylinders would be different from the mean of 4 cylinders, but at least 2 means are significantly different, and that would negate the null hypothesis. How do we do this? I will show you 2 ways. The first way is the hard way, and I like this way because it gives you an understanding of nuts and bolts of ANOVA, how this very powerful technique works. And the second way is the function or within the data analysis in Excel that will give us the ANOVA procedure in a few seconds. Let's start with the hard way and then we'll learn the easy way. The hard way is understanding that ANOVA, produces an F-test, which is the ratio of mean squares of the variation of the data sets between each of these groups, between this group, and that group, compared to the mean squares, which is the variation, of all the data points within the group, So there's definitely is a variation between the groups, because not all the groups are equal, and there is definitely, or should be, variation within each group. So the group with 4 cylinders has a variation within itself. So there is a variance or a standard deviation or a deviation from its mean. Now, this ratio or F ratio of between groups divided by within groups will give us an idea of how much of this variation in the data points is explained by the between groups by the categories of the independent variable, which is the engine size, So the bigger the between groups or the model, the more this model, explains the variation in the dependent variable, The smaller the model, the smaller the variation between the groups, the less this independent variable explains the dependent variable. So let's keep that in mind. Let's go to this ANOVA total worksheet. Still we have the same group here, and we have this formula. We have to work with the notion sum of squares, which you already should be familiar with. The sum of squares of the total data points will be equal to the sum of squares between the groups, between this group and this group and this group, plus the sum of squares or the variation within each group. So the variation within this group, 4-cylinder, and the variation within that group, and the variation within this group. So all the variations, all the combinations of variation all together will form the sum of squares total, right? So I will show you two sum of squares, how to calculate two sum of squares. Sum of squares total and sum of squares within the groups. And then algebraically, we can find the sum of squares between groups, right? Because the sum of squares between groups will be equal to sum of squares total minus sum of squares within groups. In SPSS, use, right, calculation of ANOVA, a podcast that I created earlier. You would have the formula how to calculate this sum of squares between groups, but I put that in here as well. So sum of squares between groups will be this formula here, while sum of squares within groups is a different formula that I'm going to show you just in a second, as soon as we calculate the sum of squares total. Now, sum of squares is actually each deviation, x minus x bar, squared and then summed up. So sum of squares is not really squaring the sums, it's the sum of the deviation squared. So we have to keep that in mind. So this formula right here is the definitional formula, and this SST, this formula, the second one, the bigger one, is the computational formula. We can use Excel to do either one, but I am choosing to do the first one first. So let's do this. Let's find the grand mean and the sum. The mean of all data points. Now why I'm using this? This is the sum of squares total, so I'm putting all of these columns in one, right? All of these groups in one column right here. So let's find the grand mean. If you remember in Excel, you start with an equal sign and then average, right? So in the list, you find average, double click on that, select all the data points, hit enter, and now we have the mean of all data points, otherwise called the grand mean. What about the sum? Sum is equals sum, right? So double click on the sum function, add them all up, hit enter, and this is the sum. Well, we have the mean here. What about subtracting each value now from the mean? We have to do the equal sign, the value, which is x, minus the mean. The mean is right here, grand mean, right? But you know, the next step, right, will be filling out the formula down the column. And I need to do that so that the formula copies over, but one of these factors, H24, right, is only one cell that I don't need to change. So I have to make that cell an absolute cell. So I put the mouse in between H and 24, and I hit function key F4. So now that puts a dollar sign before the H and a dollar sign before 24, so a dollar sign before the row 24 and a dollar sign between the columns. So that cell now stays absolute, doesn't really move when we copy the formula down. I hit enter, and this is the deviation of the first data point. Now I go into the autofill formula, scroll down, drag it down, and then I have all the deviations. To double check, right, I can just put and find a sum here, and that would be a 0. Okay, so that would be a 0. And we know that when you add up, all the deviation will be 0 because they all negate each other or balance each other. All right, so what do we do now here? Now we take this deviation, right, and square it, because we need absolute values. We can't work with a 0 or a negative value here. So the square is equals the deviation times itself, or as I have showed you before, you would do the little hat, holding shift and pressing number 6 in keyboard, right, hat 2, which is the cell I3 times itself, or exponent 2. So hit enter, right, scroll the formula down, and now you get all of these square deviations. I want to find the sum of that deviation, and that would be 70.67. So now that is the sum of squares total, 70.67. Okay, so that was easy. What about the sum of squares within groups, or sum of squares of error, or the variation that cannot be explained by the independent variable by the deviation or variation between groups, right? Let's go now down here to this particular sheet, ANOVA within, and I have set it up in such a way so that I can now calculate the sum of squares within groups, right? Or the residual or the error, okay? So in this case, I want to find the mean, I want to find the sum for group 1, sum for 6 cylinders, and the sum of squares for 8 cylinders. Let's do this really quickly for the first group, then I'm going to pause the movie and do the other one for the 2 other groups, and then come back. So the first one is the mean is equals average, right? So I want to find the mean of the 4 cylinders. Hit enter, so that's the mean, and the sum equals SUM. Find the sum, and that's it. Now x minus the mean is x, this data point, minus the mean for each of these data points, right? So that will be equals x minus the mean. And the mean should be f4, so that I have an absolute value. Hit enter. So that's the mean now. Fill out the formula, and I have the x mean. What about the x minus mean squared? That will be equals this deviation, little hat, 2, so squared, right? Scroll down, and now I have the sum of square for each value, but I need that sum here, so I have to autofill formula horizontally now, and I have the sum of squares for the first column. So now this is the variation, or the variance within the group of 4-cylinder engines. Let me do the other 2 groups, and I'll come back soon. Okay, so now I have calculated all sum of squares for each individual group. So this is the sum of squares within groups, or what's called the error or the residual variation inside the dependent variable. Okay. So now the sum of squares within groups will be the sum of squares within the group of 4-cylinder, sum of squares within the category of 6 cylinders engine, and the sum of squares for the category of 8-cylinder engine. So right over here in this cell, I'll be adding up these sum of squares. Equals this sum of squares plus this sum of squares plus that sum of squares. So now the sum of squares within the group will be 41.714. If you remember, the ANOVA total was 70.67. So now the sum of squares between the groups, or the sum of squares factor, or sum of squares model, right? You can name anything you want. The book has factor. Usually it's called model. SPSS calls it between groups. Any way you call it, just understand that that is the amount of variation that the independent variable explains the dependent variable. So now the sum of squares of between groups will be sum of squares total minus sum of squares within groups or error. So now that will be equal size. Sum of squares total is this number right here minus, I have to click now, I'm inside the formula. So that is the 3D formula that I'm doing in Excel. I click on the ANOVA within, right? And if you see right here in the formula bar, now the 3D formula brings up the Excel sheet together with exclamation point, right? And then I click on the cell where the sum of squares within is, right? And that cell actually is put right here in the formula bar, and I hit enter, and I go right over here, and now I see that this sum of squares between groups is 28.95. If you see sum of squares between groups is actually smaller than sum of squares within groups. Between groups explains the variation. Within groups does not explain the variation in the dependent variable. But that does not actually discourage us, because we do not compare the sum squares. What we compare is the mean square. Okay, so what is the mean square? There are two mean squares, between groups or the factor or model, and mean square of within groups or the residual or error. So mean square between groups, okay, will be equal to the sum of squares between groups divided by the degrees of freedom between groups, while the mean square of within groups will be equal to sum of squares within groups divided by degrees of freedom within groups. So now we have the sum of squares between groups and sum of squares within groups. We don't have the degrees of freedom between groups and the degrees of freedom within groups. But the degrees of freedom between groups would be equal to, okay, number of groups minus 1. So n minus 1, or equal to 3 minus 1, or equal to 2. So that is the degrees of freedom between groups. The degrees of freedom within groups will be equal to the total number of data points minus the number of groups. Okay, so I have 7 sample size in the first group times 3 would be 21 minus 3 groups. That would be equal to 18. Okay, so now another way to do that is equal to number of n minus 1 for the first group plus number of data points for second group minus 1 plus data points for group 3 minus 1. So this would be actually 7 minus 1, 6, plus 7 minus 1, 6, plus 7 minus 1, 6 equals 18. Okay, so you can calculate that in any way you want. All right, so this is really great. So now the mean square between groups will be equal to, and right here I'm going to do the formula in Excel. Sum of squares between groups was 28.95, so it's that right here, divided by degrees of freedom between groups 2. So that is the mean square between groups. What about mean square within groups? That would be equal to sum of squares within groups. That would be sum of squares within groups, which is in this other data sheet. Sum of squares within groups, that divided by I know the degrees of freedom within groups, which is 18. And now I have the mean square within groups. But what is f? F actually is equal to mean square between groups divided by mean square within groups. Okay, so f will be the ratio between this number and this number. And now I have a ratio of 6.25. So this is our f. Now what do we do with this f? We compare this to the f critical, the f that would be found when we have the degrees of freedom between groups 2, the degrees of freedom within groups 18, and the alpha level of 0.05. Okay? We actually did not specify the alpha level when we talked about the hypothesis, but we already know that because it's implied. In social sciences, the alpha level, significance level, reference probability, or 1 minus alpha is 0.05. So I'm going to get back to this f really quickly. But now I want to show you the easy way, how to find this f ratio in the easy way, and how to get Excel to give you the probability, the p-value, so that you can compare that to the 0.05. So this is the nuts and bolts. This is the real hard work of getting Excel to work for you to get the f value so that you can compare it to the f critical. Now let's work smart. with Excel. Let's go to this first Excel sheet ANOVA, right? When we had the null hypothesis and alternative hypothesis. Let me just actually write this down here. I need alpha insert equals to 0.05. I'm just going to write that down so we have it. Okay, so what is a smart way to work with Excel to get the ANOVA procedure and to find out how we can actually test this set of hypotheses? We have to go to the Data tab in Excel. All the way on the right side, you will have the data analysis. If you don't have the data analysis, please consult one of my other Excel videos about statistics, such as how to calculate R, correlation coefficient R in Excel, or other videos that I put there using Excel to put this data analysis tool in the data tab. Okay? But let's say that now you have data analysis and you want to use that to create and to conduct an ANOVA test. So in the data tab, again, go to data analysis, click on it. In the data analysis dialog box, make sure that the very first option is selected, ANOVA, single factor. This is one-way ANOVA, right? Because we have one single independent variable, and that's why it's called single factor here in Excel. Let's click OK. Now the input range is the range where we have all the data points. And as you see here in Excel, and as you've seen many times before, the data organization differs from SPSS. In SPSS, you have one variable that has all the 4-cylinder, 6-cylinder, and 8-cylinder, and that variable actually will have values. So maybe 1, 2, and 3, 1 coded 4-cylinder, 2 coded 6-cylinder, 3 coding 8-cylinder. So that would be in one variable, and all the data points will be in the other variable. So all in all, we probably would have two variables in SPSS. In Excel, you have to actually give each group its own column, right? So remember that. So the input range now will be that whole area, the whole table, right? And grouped by columns. You see, Excel actually is very robust and flexible. So if you wanted to put every data point in rows, right, with a row header, 4-cylinder, 6-cylinder, and 8-cylinder, you could do that, and then you check rows. I want labels in front rows so that Excel reads this 4-cylinder, 6-cylinder, and 8-cylinder row header. Alpha is 0.05, right? Output range, I don't want that in the new worksheet. I want it right here in this sheet. So I have to actually check the cell. So I click on that cell. That's where I want the output that Excel gives me to show. And then I click OK. Now, in just a second, ANOVA gives you the whole, Excel gives you the whole ANOVA procedure output. The thing that took us 15 minutes to calculate by using formulas and functions in other worksheets. Here's what we have. The first is the summary table that gives us the mean of miles per gallon for all these three engines. So 4-cylinder, 19 miles per gallon, 6-cylinder, 20.14, and 8-cylinder, 21.9 miles per gallon, right? And their variance. You see, this actually differs from SPSS because it gives you the variance. SPSS gives you the standard deviation. Not a big deal there, but I think this is a little bit sweeter approach actually, because since ANOVA compares the variation or the variances, I think variance is a little bit more intuitive to understand, and that's why Excel gives it to you. If you see, right, the 8-cylinder group has more variation within itself, right, because it's 3.8. Now, the most important table is the ANOVA table, where it gives you the between groups and within groups. Between groups, right, also is called model or factor, because it's how good the model or the variation between groups explain the dependent variable. While within groups is also called error or residual. Okay, because that is what does not explain the fuel economy or miles per gallon. because it's a variation within each group, right? And this total here is the sum of these two sum squares. The degrees of freedom, as we calculated for between groups, is 2, is the number of groups minus 1, 3 groups minus 1 is 2, and the degrees of freedom for within groups is all data points minus the number of groups. So we have 21 data points, or 21 samples, minus 3 is 18. And the degrees of freedom, the total would be 20, or n minus 1. The big N, 21 minus 1, 20, or the sum of these two degrees of freedom. Now, the mean square is the sum of squares for between groups divided by degrees of freedom, and the mean square for within groups is sum of squares within groups divided by its degrees of freedom, right? So this one is a ratio between this number and that number, and this is a ratio between this number and that number. Now we have another ratio, this F, the very important F, okay? This ratio here is the result of dividing the mean squares for between groups by the mean squares for within groups. Let me double check. Equals this number divided by within groups. That's 6.2466, which is this number right here. Okay, so that's the double check right there. And it gives us the p-value 0.008. This is smaller than 0.05, therefore this one is compared to the alpha level right here. Okay. So this is smaller than the alpha level, therefore we reject the null hypothesis. Okay. But what's a really nice touch about the Excel ANOVA procedure is the F critical. Excel actually gives you the F critical, the value of F that would have been seen if our null hypothesis was true, right? And that is 3.55, okay? This F critical is the F that is found in the table of critical values for F when you have the degrees of freedom for between groups 2, degrees of freedom for within groups 18, and alpha level of 0.05. So this is the critical value of F. That we will have to compare the value that we got from our sample. The general idea is that if the value that we get from the sample is as extreme or more extreme or as big or bigger than the F critical, you reject the null hypothesis. In this case, this is bigger than the F critical, therefore we reject the null hypothesis. Here's what I'm going to do just to understand this idea of comparing F values better. Let me go to this other worksheet comparing F. I have here a F distribution, right, that starts at 0 and then goes on the right side. Now, since the alternative hypothesis actually is a right tail hypothesis because it actually asks us about at least two values or two means are different, are not equal, right? We'll have to look at the right side of the F distribution. Now the F critical, right, that we would get for degrees of freedom 2 between groups, degrees of freedom within groups 18, and an alpha level of 0.05 would be 3.55. So 3.55 would be right over here in this area. So in the case when our F, the F that was found by the sample, right, is greater or to the right of this area, right, then this F of 6.25 that we found, right, from the ANOVA procedure falls within this highlighted region here called the rejection region, because our F is more extreme, is bigger than the F that would be found if the null hypothesis were true. So if the F critical, right, that is right here in 3.55, this is the area, this is the line, and to the left, right, means that the null hypothesis cannot be rejected because we could have some probability that the null hypothesis could be true. But if the F critical is greater, is to the right, is to the extreme side of 3.55, which is the F critical, then we reject the null hypothesis, meaning that the probability that our F is 3.55 or smaller is very, very, very small. In that case, we reject the null hypothesis of no significance between the means of 4-cylinder, 6-cylinder, and 8-cylinder, and we accept the alternative hypothesis where at least two means are significantly different. Right? At least two means are significantly different. Two things I want to show you at the end of this podcast. One is that there is no built-in function for ANOVA in Excel. So if, for example, I were to go here and type in equals ANOVA, there is no such function, right? So ANOVA, there is no function like that. So there is no built-in function. You have to have the data and then the data analysis tool, okay? The second thing is that for paired analysis, such as Bonferroni, Toki, or Sheffi, right, which is finding out which one of the pairs of these groups actually is or is not significant, right? In Excel, you have to really go beyond Excel Advanced and use some really sophisticated formula that I am not going to cover in this podcast. Okay, so in this podcast, I showed you only how to use Excel with its own functionality to get the sum squares total, sum squares within, and then find the sum squares between groups, get the ratio of the mean squares between groups and mean squares within groups, find the F, and with the F compare with the F critical, and then reject or fail to reject the null hypothesis. And then I went on to actually give you an idea of how you can use data analysis to get the ANOVA procedure straight into Excel. Okay, and then we found the p-value, we rejected the null hypothesis in our case, and we accepted the alternative hypothesis that showed us that there is sufficient evidence to show us that at least two means are significantly different from each other. Okay? I hope Excel is a very good tool in case you don't have SPSS. All right. Good luck.